Hello everyone, and thank you for registering to watch this Kingdom webcast on uncertainty and risk reduction in depth conversion, available within VelPAK for the Kingdom 2015 release. My name is Kathy Cowley and I work for Equipoise Software Limited, who develop VelPAK on behalf of IHS. Before we begin, there are a couple of housekeeping items I need to make you aware of. Firstly, make sure your speaker volume is up so you can hear clearly. Secondly, there is no telephone dial-in this webcast. It is audio only, which means if you ask a question, I can't hear you. Any questions that you do have, there is a Q&A window on your screen, which you can type questions into. We will get back to you with answers either during the webcast or shortly afterwards, depending upon the complexity of the question, as we have your email addresses recorded from registration. Okay, so let's get on with the webcast. Today, we are looking at uncertainty and risk reduction in depth conversion available from within the VelPAK package, and how you can quantify this and use the information to mitigate against misplaced wells and targeting the wrong parts of the reservoir. We can use the information for improved reservoir economics, asset evaluation, forecasting, and reservoir monitoring. A look at this graph, albeit somewhat old from the 1990s from the Norwegian North Sea, displays forecast recovery size on the x-axis versus actual discovery size on the y-axis. The vast majority of forecasts fall well below the central blue line, meaning expected discovery size is sometimes vastly greater than the actual discovery size. Note that this graph is logarithmic too. The mean of actual discovery sizes equals, in this case, about 38% of the sum of the forecast discovery sizes, with the biggest driver of overestimation being gross rock volume, GRV, driven by oil-water contact assumptions. This slide shows a tornado plot of volumetric uncertainty. When we are calculating in-place volumes for either oil or gas, we are multiplying the GRV by a net to gross, a porosity, a saturation, and a formation volume factor. Although there is uncertainty in all of these parameters, it is almost always the case that the GRV has the most uncertainty. Porosity, for example, can only change by a few percent, while the GRV can be hugely different depending on a varying oil-water contact. So, if we really want to know how small or large our oil or gas field can be, we need to have an idea about the variability in the size of the tank. So, how do we do this? Well, there are three things that can change that will make our trap smaller or bigger. There could be an alternate top-base reservoir two-way time pick, and in 2D data there is also an uncertainty between lines. There is usually questions about how thick the reservoir could be away from our wells, and there is the variability of the trap size that relates to the velocity model. Velocities in wells can often be thought of as hard data points, and the velocities generated from sonic tools considered accurate, although there are a number of situations where they are not. Also, as wells are rather expensive to drill, we don't have many of them around, so laterally this kind of velocity data is rather sparse. Typically, there is limited well control over an area, and quite often the well placement is biased, for example on structural traps. Well data is the classic territory of velocity function derivation, which describe over specified intervals how velocities change with the parameter, often depth. And these functions are combined with the two-way time surfaces to create a deterministic depth conversion. But even though we can fit a function to velocity data, there is a degree of uncertainty about how the velocities can change both laterally and vertically as soon as we move away from our control points. VelPAK's newest module, the Analyze module, uses Monte Carlo stochastic modelling to make multiple depth conversions with stochastically wobbled parameters from a best-case depth conversion that bring in these uncertainties and produce a range of results, all of which tie to the well formation tops. So how does VelPAK do it? Well, a standard part of VelPAK has always been in fast and accurate constructions of depth conversion models, incorporating seismic and well interpretation data, well log velocities, seismic velocities, parametric functions, or a combination of the above. The Analyze tool enables a user to develop a reasonable estimate of depth uncertainty based on a large number of depth models derived from one or more depth conversion schemes, and allows a user to identify key parameters controlling the range of gross rock volume. An absolute answer to the depth conversion problem is impossible, but the loop depth conversion processes available in the workflow system will generate multiple depth conversion models. In this slide, to the left, a single standard workflow has been set up, which records details of the depth conversion within VelPAK. To the right, there is a looping workflow, which loops through the process, wobbling key parameters, generating multiple depth converted models. Once it goes through to the end, it then goes back to the beginning again. Typically, at least 500 models will be run, and statistics and volumes for each well, for each layer, and for each volume will be stored in the form of easily analysed data grids. Data can also be output to Excel. The statistics, volumes and parameters for each realization are recorded. And as you will see later, the animation option of the Analyze module will capture snapshots as required, so a cartoon can be run to watch the range of reservoir sizes or any other displays of interest. All the parameters of each model are saved such that any particular realization can be recreated by calling up the model number as required. The Analyze module then allows filtering and analysis of the results and gives confidence as to the likely range of uncertainty in the model and the deterministic parameters which will yield credible P50, the most likely, and endpoint P10, P90 solutions. P10 being the highest figure, with which 90% of models are smaller than this, and P90 the lowest figure, meaning 90% of models are larger. VelPAK uses two main approaches to developing the uncertainty data for use in the analysis module, which can either be used separately or in combination. Firstly, there's parametric variation, investigating depth variation resulting from changing the function parameters in a deterministic model. And secondly, there's lateral uncertainty using kriging. We'll look at lateral uncertainty using kriging in a moment, but here, moving to the next slide, we see two example animations of parametric variation, one a wobbled regression display and the second one a wobbled optimization. Regression is appropriate for linear relationships of velocity depth or time depth, the classic V equals V0 plus Kz, for example, where Z is depth and V0 is the intercept on the y-axis. Confidence bands can be applied to linear regression, for example at 95%, and we can wobble the regression within those bands. Optimization is another approach to deducing parameters to a given function, but it will work with nonlinear equations too. In addition to the best fit, optimization also results in a solution trough where pairs of parameters nearly satisfy the equation. So, moving on to lateral uncertainty using kriging, regression and optimization typically perturb the model vertically by squashing and stretching, but we can also exploit the error in gridding to give spatial variance in map construction. Typically, this is done through kriging using sequential Gaussian simulation. This is when the gridding parameters are perturbed to allow simulated surfaces that have identical statistical properties as a best grid surface. They still honour the control point, but have different shapes. For example, this profile has been picked, but on the left there is very little detail to go on as to whether the pick is correct. It could arguably be picked higher or lower. SGS adds uncertainty to an interpretation pick, using it to perturb the variogram parameters to add realistic levels of noise. This next slide shows an animation of a map, in this case velocity, holding identical statistical properties as the best case gridded surface, still honouring the control point data available, but having different shapes. This animated set of maps have once again been generated through wobbling lateral variation using kriging with SGS within the looping course of the VelPAK workflow system. We have seen this picture before of a histogram of a distribution of positive volume on a VelPAK workflow run producing 500 models. As well as the P10, P50 and P90 points, the line of grey blobs or circles is the probability distribution function, or PDF line, for the model. Each circle is the value of positive volume calculated for one model, so in this case there should be 500 grey circles on the display. As well as wobbling around the uncertainty of an oil-water contact to produce a range of positive volumes, VelPAK recognises that the spill point for a structure could be very different for each realisation. The spill point is the structurally lowest point in a hydrocarbon trap that can retain hydrocarbons. Once a trap has been filled to spill, further storage or retention of hydrocarbons will not occur for lack of reservoir space within that trap. The hydrocarbons spill or leak out, and they continue to migrate until they are trapped elsewhere. If the structure is filled to spill, then the spill point and value will vary from each depth realisation. VelPAK automatically calculates the spill point and calculates the height above surface accordingly. Phase 1 is VelPAK calculating the initial height above contact surface, showing all possible accumulations. And then Phase 2, VelPAK enables a user to flood any accumulation by using an existing well or choosing a target or seed point. Here is an animation available from within VelPAK showing the fill to spill animation of the various realizations produced. The final feature to present here is a sensitivity analysis which can be performed to determine which are the key parameters controlling the maximum variation in the reservoir volume variation. It enables a user to see at a glance on a spider plot which parameters have contributed to a big change in the generated value for the volume and which have not contributed so much. So, the new risk reduction module of VelPAK can help answer questions about the probability distribution of gross rock volumes in your prospect, the key parameters controlling the range of gross rock volume, the spill point depth for fluids in the prospect, and how multiple prospects can be connected if the fluid contact depth is uncertain. So that is the end of this part of the presentation. I am now going to hand you over to my colleague Adrian Brain, who will give you a demo of the Monte Carlo method of uncertainty and risk reduction in depth conversion within the VelPAK software itself. Just to confirm, if you have any questions, please use the Q&A window on your screen, which you can type questions into. We will get back to you with the answers either during the webcast or shortly afterwards. Over to you, Adrian.
Well, thank you for that informative and lucid introduction, Kathy. I'm now going to lead you through a worked example with real project data that shows these concepts in action to demonstrate just how easy it is to generate multiple realizations and analyze the results in VelPAK. The results will show how important it is to perform this type of exercise to meaningfully quantify and hence reduce the risk in prospect evaluations. I'm using a Kingdom 2015 Feature Pack 2 release of VelPAK, which has an updated 3D visualization tool. All the other tools I'll show you are available in the current Kingdom and VelPAK release. For this demo, I've chosen to use the same data that we use in the VelPAK training course, as many users of VelPAK will be familiar with this data. If you have attended the VelPAK training course and you have your saved models, it should be a simple procedure for you to load up that data and to start running Monte Carlo simulations using the procedure I'm about to show you. The data is provided courtesy of Shell UK and comes from the Gallian gas field in the southern North Sea. The gas is in a traditional structural trap under the base of the Upper Permian. We can see this on a profile through the centre of the survey. So our gas is trapped under the Upper Permian event through here. If we look at the section, we can see some push down of the surfaces under the upper extensional structure. So we need a careful depth conversion method to remove these artifacts to get good volumetrics. A single depth conversion can be used to give us our best deterministic gross rock volume, but we would really like to quantify this in terms of proven, probable, impossible volumes. We would also like to examine the data to see how accurate our deterministic depth conversion was, and are there any other factors we should be aware of when estimating the reserves. Now, our starting point should of course be our best technical case depth conversion. That is, we make a single depth conversion utilising all of the information to hand, ensuring all the information ties and calibrates with each other. In our case, we have a 4-layer depth conversion. I can show you a typical well from the centre of the field. We'll use this well to define our velocity functions and our depth conversion methods. The first layer, from the datum down to the upper Triassic, shows a clear linear velocity gradient. So I've opted to use a traditional V0K depth conversion method. Now, VelPAK has two ways of generating the V0K parameters. We can use the curve tool to make a linear regression through the well velocity logs for the layer in question, or we can use numerical optimization, which is a more robust and ultimately more useful approach based on Mac al-Chalabi's famous method. I have opted to use the optimization procedure as we can exploit the non-uniqueness of the V0K solution. I've used an optimization method that minimises residual error. That is, we find V0K parameters that result in a zero error between the depth converted surface and the well formation top. On the display, each well is presented as a blue curve, and at any point on the blue curve, for each well, the corresponding V0K values will result in a zero residual error. The results for each well are combined to give the cyan curve here. I can turn off the residual lines to show the resultant solution trough for all the wells. This is the region in which any V0K parameter pair will give the same misfit between the predicted surface depth and the corresponding formation top. In this case, our solution trough has an RMS residual of 21 meters, so any V0K pair in that space will have an RMS error of less than 21 meters. When we come to run the multiple realizations, we can specify any contour value within which we can randomly choose V0Ks for each realization. I've also chosen to use optimization for V0K parameters for the second layer. So that's our layer from the upper Triassic down to the lower Triassic. Again, we have a different solution trough here, about 26 meters. Seems to be the central trough. We can reduce that window, of course, when we come to do the multiple realizations. Now, if you've attended the VelPAK training course, you may recall we use stacking velocities calibrated to well velocities for depth converting the second layer, but they were used more for the purpose of training than for the best depth conversion. We could, of course, use the stacking interval velocities and perturb the gridding using sequential Gaussian simulation for each of the surface realizations as an alternative, as Kathy described earlier. But I'm going to use the optimization method in this case. Now, the easiest way to run optimization is through the workflow system, so I'll quickly build a workflow for the first two layers. It's always easiest to start with a template, delete what is not required in the template, and then add in what you need. I'll arrange the workflow horizontally to make it easier to see what's going on. Delete what's not needed. And start plugging in the pre-built workflows. So for the first layer, I'm going to use a depth convert using numerical optimization, a V0KZ method, and I'm going to use a minimised residual for layer 1. For the sake of interest, I'll use a slightly different optimization method for layer 2, and I'll fix K. Patch the workflow together. Now we have 2 more layers to do, so I'll bring in the event nodes for layers 3 and 4. Now if we go back to the well display, the 3rd layer exhibits fairly constant velocities through the layer. So in this case we'll just grid up or map the well interval velocities with a view to perturbing the gridding of those velocities for the multiple realizations, giving us lateral variation without changing the vertical stretch at the well locations. Now of course we have a pre-built workflow for this, and this is found under depth conversion, mapping interval velocity. So I'll just drop that into our workflow. Now our 4th layer forms the cap on our structural gas trap. This consists of high velocity anhydrite rafts floating in the lower velocity helitic layers. We can see these effects in the logs. In this well we have a high velocity bust here. If I step back a couple of wells, there's another well where we have 2 of these velocity busts. Now, we have seismic velocities in the model. What I can do quickly is generate some pseudo wells from the seismic velocities. And I'll make these at the well locations. I can now overlay the pseudo wells made from the seismic velocities over the corresponding real well. This is well 4815A5, so I find the corresponding stack well. The red curve is the overlay well from the seismic velocities. We can see that the seismic velocities simply don't see these faster anhydrite layers. However, on the seismic section we can see the layers thin and thicken considerably, dependent on the presence or absence of the faster anhydrites. This layer is going to be tricky to depth convert, and we have to adopt a pragmatic approach that cross-plots well interval velocities against the isochron. Before I do that, I'll just delete all the pseudo wells because they're not going to be of much use to us here. So I can go ahead and make sure we're on event 4, and I can make a plot of the isochron versus the well apparent interval velocity. When we come to run the multiple regressions, we can wobble this regression line within the confidence bands. So I can turn on the confidence bands. Here we'll just use a 95% limit, turn on the bands. So the black regression line will fit always between the blue and the green bands. Once again, I can add this method to the existing workflow. We have a pre-built method for this. So it's curve fitting, interval velocity versus isochron. Drop that into our workflow. And then I can run the workflow. I'm going to detach the workflow window before I hit the run button. I'll just save this workflow as base case. And set it running. And we'll have a 4-layer depth conversion using our methods. can go back to our profile. I'm going to toggle that out of the way. Go back to our profile. We can depth convert this now. To depth convert the horizons and the grids, we've got an issue at the edge. So we can see a time domain plot. Then we can look at it in the depth domain. So notice in the depth domain, these layers that were pushed down in the time domain have been flattened. So we've taken into account the faster velocities due to the shallower extensional stretching, which suggests we have basically a good depth conversion. We can also look at our residual errors on the surface map. I'll just clean up the map display so we can read the values. We have residual errors of about 20 meters, 7 meters, 6 meters, 1 meter, 10 meters, thereabouts, ballpark. So a reasonably good depth conversion. So before generating multiple realizations, we should really consider our structural trap and see how we want to assess it. I can display the depth grid for the top of the structure on the surface map. Now, assuming a gas-water contact of around 2,550 meters, I can quickly manipulate the color table to preview our structure above the contact. So we're looking at a window of about 2,300 to say 2,550, which is our guesstimated gas-water contact. We can see the structure above the contact, and this gives us a series of isolated bodies. And we can see that they're going to be approximately 250-300 meters in thickness. So when we run multiple realizations, we can actually use the filter spill routine from a seed point on the structure, which is typically a well location, to isolate connected geobodies for more accurate and useful volumetrics. So all we need to do now is adapt our workflow to run multiple times. Before I do this, I'll just set the display parameters back to automatic. The procedure actually initially appears quite complex, but is in fact fairly simple. Of course, we have an example workflow on how to adapt a single depth conversion workflow into a looped workflow that we need. So this example workflow built into the software has an example 4-layer depth conversion, and it shows you how to modify that into a looped workflow. What we need to do is add two nodes, the Analyze Stats Start and Analyze Stats Initialize nodes, before we actually do our first depth conversion. Now, of course, these nodes are all in the nodes flyout, but it's usually easier just to copy these nodes from this example workflow. The main change to the workflow, which if I zoom out becomes clear, is that we add a loop around the main body of the workflow. And to do this, we just use a loop node that forces the flow around and around until some condition is met. Now we can parameterize the number of iterations by clicking on the loop node, opening a parameters flyout, and setting a value. 1,000 iterations is good. 500 is also useful, but don't go below 500 is my suggestion. Then, after each layer, all we do is record the statistics for that layer. Now, if you're not perturbing the parameters for a particular layer, which is quite reasonable to keep some layers perfectly constant, you don't need the Analyze Stats Record node. If you do put it in, the statistics are recorded. Now, after the fourth layer, which is the top of our prospective reservoir, we also compute the volumetrics we set up using this node, Analyze Stats Volumetric. and open the model node, the model parameters for the node. And what we can do is say, yes, we want to record statistics. We want to nominate a location as a seed point for a spill. We're using a filter spill method, 4815A5, I believe. We can specify the units for our statistics, such as acres feet, but I'm going to do it in million cubic meters. Additionally, we can provide a base grid and we can provide a contact for volumetrics, but we're using the filter spill routine. So I've adapted my workflow already, but for our fourth layer I'm also going to make a height above display, and this records an image of the surface above the spill point. This is useful for QC purposes and also for generating animations, which we'll see later. We can parameterize this display at runtime. Other displays can be found under the workflows, write your own workflows, components, display folder. So you can display lots of surface information there. Now for this layer I'm also going to save the height above the spill point and depth grids that are computed in the model, as I'd like to do some statistical analysis on them later. Finally, right before the end of the workflow, we need an analyze stats end node, at which point the workflow collates all of the recorded information for each of the 1,000 models in a digestible format for interpretation. So the workflow is ready to run, but before I do so I'm going to detach the workflow window before executing it and move it off to the side. Actually I'll shrink it down, see if we can fit it into small space, and set it running. The first time through, which is our loop 0, it runs the base case depth conversion, which we've already seen. Now I've added some extra nodes to the workflow, so it's the height above display and the save grids options. So I will be expecting a few prompts from those nodes to configure the software as to how I want it. So I want to display and record the height above image because I'd like to animate those later. So I'll say yes to that, and then it asks me to configure the height above display. Now we're plotting a height above spill grid, and my earlier quick look suggested a useful thickness of 200 meters to 250 meters or so. So I'll be conservative and give it a Z-min and a Z-max range of 0 to 300. And I'll also choose a colour bar. I quite like my soft palette, so I'm going to use that palette there. Toggle on do not ask again. Press OK and OK to remove any existing grids from previous runs. Now the second time through the workflow, we've been through once, remember. Second time through, the software realizes, well, we're doing this again. Do I want to randomize the variables? In the case of optimization, it's going to prompt me for a range of residual errors. So, in this case, I'm going to have small residual errors between 0 and 16 meters. 16 meters is the maximum error I'm going to allow. For the second layer, I'm going to use a slightly larger range, 0 to say 25 meters. Now for the third layer, we're creaking up the well interval velocities. So I can't stretch and squeeze that layer vertically, but what I can do is perturb the gridding to give some spatial variation within the layer. I'll use quite a big range. So I'm allowing variation between 40,000 meters and 50,000 meters on the Kriging range randomization. And for the final layer, whereby we had a linear regression between interval velocity and the layer time thickness, we can wobble the regression line within a confidence band. The software defaults to 95%, and I'm going to stick with this. So we set the linear 95% there, press OK. So the workflow carries on. Now the third time round, the workflow has all the information it needs and it can run unattended. Now as you can see, it takes around a minute or so for one realization. So 1000 realizations on this machine is going to take about 16 hours to run. Ordinarily you'd run the work job in batch mode, whereby the job is divided up by the number of CPU cores you nominate to use on your machine. So on an 8-core machine, the elapsed time would go from 16 hours down to about 2 hours. However, even that is too long for this webinar, so I've run the job already and can load the model now. So I'll hit escape to stop this job, and I'll reload my previously ran model. So in the Analyze tool, we see a series of tabs. We'll take a look first at the Summary tab. Here we can see our base case depth conversion and the methods used for each layer. So we see our Optimize methods for the first two layers, the gridding of the interval velocity for the third layer, and the interval velocity isochron method for the fourth layer. And underneath we can see how these layers are randomized for the multiple realizations. Now let's take a look at the Data tab. Here we have collated results for each well for each realization. The first column shows the model number, so going from 0 down to 1000. And we can see we have residual errors, well isochrons, isopachs, apparent interval velocities, lots of other juicy information for each well, for each of the realizations. If I scroll right across, we can see a POS volume column. In this case, the POS volume is the gross rock volume above the fluid spill point. These tables can of course be exported as spreadsheet files or copy and pasted into Excel, but it's easy to graph the results in VelPAK using the Graph tab. Just like the Curve Fit tool, we use the Generate, Standard, Flyout to specify the graph we'd like. Now here I've already generated the histogram of positive volume. The x-axis are those specified in the statistics flyout we've seen before, so those are in units of millions of cubic meters, versus the number of models in those ranges. So here we have a peak volume of between 5,600 and 6,000 million cubic meters. We can use the display flyout to adjust the number of bins. I'm going to bump this up to 20 bins. Press apply, and we immediately notice that there is some evidence of a slight bimodal distribution. We'll use some of the other tools available to investigate this and explain this shortly. I can also plot the probability distribution function on the histogram. Each realization is plotted as a grey blob on this curve, whilst the P90, P50 and P10 points are plotted as red blobs. The P90 point is often called the proven or proved volume, and 90% of estimated volumes will be greater than this value. P50 is the mean volume and represents the most likely volume, whilst P10 is the possible volume, although only 10% of volumes are likely to be greater than this value. We also plot our M0 value, which is the model volumetric for our best technical case starting model. In this example, it's interesting to note that what we consider to be our best technical depth conversion is rather optimistic, which correlates with the statistics Kathy mentioned earlier. So why is this? Well, we know our depth conversion methods are good. They were accurate to within 10 meters or so at predicting the depth at well locations. We need to actually take a step back and look at the data we've used for the analysis. So let's take a look at the top of our structure grid and plot the wells on our map. And here I'm going to use our new 3D view. If I rotate the display, so we're looking down the axis of this structural high, we can see, not unsurprisingly, all of our wells are drilled on the structural highs. So, the well data we are using for our analysis is inherently biased towards the higher volumes. So had we just taken our best technical case depth conversion on its own, all the indications would suggest we have a volumetric computation overestimating quite considerably. Here the positive volume is 6,738 million cubic meters, whereas our P50 volume is considerably less, maybe 20% less, down at 5,780. Remember in the workflow I saved images of each of the depth surfaces. We can animate these using the Anim tab. And the Anim flyout. So we can see each of the models and the corresponding surfaces. I'm going to abort this animation. There's quite a nice, useful display. But if I go back to the Data tab and click on the column header for the positive volume column to sort the data, initially from low to high, but then we can sort from high to low, but I'll go low to high. I can then return to the animation window and rerun the animation. And this runs the animation in terms of surfaces of ascending volume. So if we watch the animation for a while, we can see why there is a slight bimodality in the lower volumes. We see towards the bottom there's sometimes a structure that is connected and other times not connected. And again, in the northeast we have a structure that's sometimes there, sometimes not. To test how isolated these structures are, it'd probably be a good idea to rerun the 1,000 realizations, but using seed points on the centres of those structures, and that will give us a better clue as to the connectivity with the main structure. And this could be quite influential in determining the volumetrics of a particular target and whether the traps are connected or not. I will stop the animation. Remember I saved some depth grids in the workflow? Let's do some maths on these. On the Statistics tabs, I can run some stats on our height above grids. So I can compute the minimum of those grids, the maximum, the average, the standard deviation. But what I'm going to do is run the percentage above grids. So it sums all the grids up and then works out what the percentage contribution of each at any one particular location is. And this is going to give us a probability of closure map. Now it takes a few minutes to run, so I've pre-ran this and stored the grid in our General 01 slot. So if I go to the surface map, display our General 01 grid, Here's a probability of closure map, or a percentage above zero map. I'm just going to change the display range from 0 to 300 to 0 to 100, because these are percentages. So if I go to point pick mode, if I go to point pick mode, I can hover the mouse over the probability of closure map. In the centre of the structure, it's 100% certain we are in the volume there. On these flanks, up here, we have a 40% chance of that structure being present, and right down here, we've just got a small percentage chance of about 2% chance of that being hit should we drill there. Turn off the tops to make it easier to see. Now, there are additional tools within VelPAK risk reduction we can use to analyse the depth conversion. One is the lever analysis tool, which allows you to look at the sensitivity of the depth conversion parameters versus the volumetrics. This can often help determine the most important parameters in the depth conversion, and also which are the least important parameters. These can help focus attention on those relevant parameters to improve the depth conversion model. We don't have time to go into that at this moment in this webinar, as we're rapidly running out of time. However, I think that should give you an overview of how easy it is to adapt an existing workflow for multiple realizations. The software takes care of all the randomization, it prompts you for the ranges of values, and then generates a whole series of realizations. You can then use the various analytic tools to look at the data in different ways, try to understand what's going on, and end up with our final product of the P10, P50, P90 distribution. Which is of key value to all of the reservoir economics. So thank you very much for attending. Please check the IHS website for other webinars in this series. There is another one on a new feature of VelPAK 2015 called the High Definition module, which is generating high definition velocity volumes. And also there's one on the new Kingdom Seismic Inversion, which you may find interest, which is also developed by Equipoise Software. You can also check the Equipoise Software website for further information on these products. Thank you very much for attending. If you have any further questions or technical support on the software, here are the email addresses you can use to contact either IHS, or for VelPAK and inversion specific issues, you can contact Equipoise Software directly, and we'll do our best to help. Now, Kathy's flagging up that we've got some questions coming in, so thank you very much for those. If you could hang on just 30 seconds or so, we'll start collating the questions and we'll be able to answer them very shortly. Please bear with us. Thank you. Okay, so this question has come up and it's been asked by a couple of attendees to the webcast, and it's also a frequently asked question by our users of the software. Can you randomize the gas oil or the oil water contact for each realization? Well, yes, you can. In the demo, you'll recall I used a filter spill volumetric computation, but you can easily perform volumetrics down to either a constant value or a grid. Now, if you're using a grid, which could of course be flat, you can randomize the grid value between a range of depths. So, for example, in this project, I could randomize the cutoff grid between, say, 2,400, 2,600 meters, and that might have been a good range. So yes, you can randomize the fluid contact. Here's another question. Can we make a velocity volume for our P10, P50 and P90 cases? Again, the answer is yes, you can. You could technically do it in the workflow, but if you're making 1,000 iterations, you really don't want to be generating 1,000 velocity volumes. So what VelPAK does, it stores all the parameters required to recreate any particular model, so it can be instantiated very quickly. All you have to do is specify the model number at the top of the workflow window and then simply run the workflow. The software knows only one realization is required, so it doesn't start looping, and after completion the model is set to that realization. There are handy shortcuts to generate the P90, P50 and P10 models in addition to the best technical case, so you can reset the model back to your deterministic depth conversion very quickly. Once the model has been instantiated, you can then generate the seg-y velocity volume and export the depth surfaces to Kingdom for that particular model. So yes, you can make velocity volumes for your P10, P50 and P90 cases. A question here on what other volumetrics can be calculated. Well, at the moment VelPAK only computes gross rock volume. If you want to factor in net to gross ratio, porosity and all the other factors, you can do so, but this will be done in the Kingdom Volumetrics and Reserve Estimation tools. There's two places in Kingdom and Kingdom Advanced you can generate these volumetrics. All you need to do is export the appropriate grids from the VelPAK model back to the Kingdom project tree and then use those functions. I will say that, as Kathy touched upon in the beginning of her presentation, gross rock volume has by far and away the biggest influence on reserves estimation. All the other factors typically only vary by a few percentage points, so changing porosity from say 20 to 25% isn't going to make such a huge difference as the initial estimation of the gross rock volume. Oh, and also I should say that although I didn't do it in the live demo here, you can incorporate one or more polygons into the volumetric computation. And another question, we'll make this our last question because I know we're running out of time. Can I export the probability distribution function for use in our company's risking package? Yes, the probability distribution function is part of the data table. Remember I showed you those big spreadsheet views of the results of the multiple realizations? Well, it's one of those columns in those data tables. So you can export the whole data table to Excel and then extract the probability distribution function from there. And you can also run analytics on some of the other columns of the data. There's lots of useful information there. Okay, we have some other questions. What we'll do is we'll start to answer those by email. Thank you for asking them, and we'll get back to you within the next few days with answers to those. But thank you once again very much for attending this webinar. Thank you. And we'll sign off now. Okay? All right, goodbye.